Today our next topic in our interference concept is interference in thin films. Okay, from up to last video we discussed about superposition of waves and interference of light and what are the conditions that are mainly for the interference. Now let us see what is the interference concept in thin films. See here, interference in thin films. So what is meant by interference? Simply we said superposition of two or more light waves. Now when the light is incident on a plain parallel thin film, some portion gets reflected from the upper surface and the remaining portion is transmitted into the film. Again, some portion of the transmitted light that is reflected back into the lower surface and emerges through to the upper surface. So these reflected light beams superimposed with each other produce interference and forming interference pattern. The best example for the interference of thin films. What is the thin film means? The general example is we saw in rainy seasons. That means on roads we saw the pattern by the illusion of sunlight. There we see the interference pattern due to spectra colors. That's the visible region colors. But whenever we are using a monochromatic source, then we get the bright and dark fringes only. When the film is illuminated by a white light, then we can observe the Vibgyor colors. Okay, so thin film means let us take some water and pour one drop of oil, whatever that may be kerosene or oil. There is a layer between that water and oil drop. That's known as a thin film. So we are talking about that type of thin films whenever that is exposed to a monochromatic light here. So what happens when it exposed to a white light? We will discuss about that later. Now let us see interference in thin films due to monochromatic source of light. See here. Here we are considering a film of thickness T and the refractive index of the medium is a mu, and what actions that we are done in the film, let us see. So consider a transparent plain parallel thin film of thickness T and refractive index mu. What is meant by refractive index? Means it is the ratio of velocity of light in a vacuum to the velocity of light in a particular medium, specified medium. So here the thickness of the film which we are considering is T and the refractive index is mu. Now a monochromatic light ray AB that is incident at an angle I on the upper surface of the film. Here it is a monochromatic source. It is a monochromatic source and AB, the incident ray is AB. It is incident on the film with an angle I on the upper surface of the film. Next, so BN and BC are the reflected and transmitted rays. See here, BN that is the reflected ray and BC that is the transmitted light rays. Now this BC is the incident ray for this lower film. BC that is the incident ray for this film. That means the lower surface. Okay. Now the angle of refraction is R. The ray BC will be reflected into the film and emerge to the film in the form of a light ray CT. Now AB is incident for the upper surface. BC is the refracted ray and BN that means R1 is the reflected ray. And now This is the BC. The BC is the incident ray for the second surface, that means the lower surface, and CD is also the refracted ray which emerges through the upper surface, and this T1 is the transmitted ray. Okay, let us see what is the phenomena occurred inside the film. So to know the path difference, we draw the normal DN to BN. So how much path difference will be from the incident ray to the final reflected ray means, that is the path difference. So to know that, we have to draw a normal from D to N, that is the dn to bn, that is the normal. Now what is the path difference? The path difference between the two light rays, two refracted rays R1 and R2 is delta. Delta equals to mu into BC plus CD in film, BC CD in the film, and Bn in the air. That means within the medium. So we are considering two mediums here. One is the rarer medium and denser medium. Rarer medium, this is the example for the air, and denser medium, this is a glass or water. And here we are considering a film, and this is the denser medium. That means the point of reflection B that occurs from the denser medium. Now the path difference becomes inside the film. That means BC plus CD within the film and Bn in air. That is the path difference. So whenever we are subtracting the BC plus CD from this Bn, we get the total path difference. Let us see. Now we are considering a triangle BCM. So here is a triangle BCM. So from that, cos R equals to Cm by BC. Cos R equals to Cm by BC. Now BC equals to, we already know that here thickness T, that is along with the Cm. Okay, so now the Cm value becomes T. Now BC equals to T by cos R. And next, from triangle CDM, that is beside the BCM triangle. So from triangle CDM, here also we can consider the cos R, that equals to Cm by CD. Again we know the Cm value. From here CT we have to know. And from triangle BMC, that means we are considering the first triangle again for the tan value. So tan R equals to Bm by Cm. Now Bm becomes T tan R because Cm is already, no, that's the T tan R. And now MD. MD value also from this triangle is T tan R. Now Bm plus MD. See, from B to D we are considering that Bm plus MD. So Bm plus MD equals to 2T tan R. Now from triangle B and D, that means the path difference in the air medium, Bn, triangle B and D. Now sin I. What is the sin I? So sin I is here, that's the Bn by BD. Bn by BD. BD is the hypotenuse here. Okay, and now Bn equals to BD sin I. So BD, we have to write BD like a Bm plus MD sin I, because we know the values of Bm plus MD, that's a T tan R. T tan R plus T tan R becomes 2T tan R, that into sin I. And next, we know the Snell's law very well. That is the actual Snell's law is mu1 sin I equals to mu2 sin R. That means one is the rarer medium and the other is the denser medium. So rarer medium, the mu value is 1. That is the air refractive index is 1. So we are considering sin I and mu2 is considered as mu. So sin I equals to mu sin R. Now Bn equals to 2T tan R. Instead of sin I, we write here mu sin R. So the total path difference is 2 mu T cos R. That means In this slide, we are the BC and CD values. Here we have the BC value, and in the next slide we have the CD value. Now the path difference is the BC plus CD in the film. So 2 mu t by cos r minus the Bn, that is the in air path difference. So total becomes 2 mu t cos r into 1 minus sin square r. So 1 minus sin square, we can write it as cos square r. So finally we get the path difference 2 mu t cos r. So here the point B reflection occurs from the denser medium, because that's the glass we are considering the film, that is the denser medium. Then the light ray undergoes an additional phase change of phi or path difference of lambda. Okay, so whenever it is reflecting from denser medium, it definitely undergoes a change, that is a phase change or a path change, that means path difference. So we are considering the phase, we can write it as pi, and we are considering as path difference, we can write it as lambda by 2. Now the total path difference 2 mu t cos r, that is plus r minus lambda by 2, because here we are considering the path difference and here also we are taking the path difference lambda by 2. And now let us see what are the conditions for bright and dark fringes. Because we are using a monochromatic source, we can definitely get the alternate bright and dark fringes. Okay, so let us see what are the conditions for the bright and dark fringes. Okay, so when the path difference is equal to the integral multiple of lambda, then the light ray meet in phase and undergo constructive interference. So I already said that whenever it is a construction that undergoes, that means the adding of the waves, wave amplitudes, so that undergoes the constructive interference. Okay, so now the path difference is equal to the integral multiple of, that means the even integral multiple of lambda, then the light rays undergoes constructive interference because they are meet in phase. Okay, so the condition for bright fringe is 2 mu t cos r plus lambda by 2, that equals to n lambda. So n is the even integral multiple of lambda. So from here 2 mu t cos r equals to n lambda minus lambda by 2. So 2 mu t cos r equals to 2n minus 1 into lambda by 2. Let us see what is the condition for dark fringe. See here how the bright and dark fringe alternately appears. Okay, and now when the path difference is equal to the odd integral multiple of lambda, then the light ray meets out of phase and undergo destructive interference. So 2 mu t cos r plus lambda by 2 equals to 2n plus 1 into lambda by 2. So from here we have to write 2 mu t cos r equals to 2n plus 1 into lambda by 2 minus lambda by 2. So 2 mu t cos r equals to n lambda. So depending upon the above conditions, the interference pattern consists of bright and dark fringes consequently. And next we are discussing about the colors in thin films. We already know that is depends upon the colors in thin films means the light, that means the film that is illuminated with the white light. So in white light we have the 7 colors. We already know, we are very well known about that 7 colors. But the intensity of the color is depends upon the thickness of the film and our eye, okay, and the refractive index. So let us see what is the colors in thin films concept. See here, this is the colors in thin films concept. See, we usually see this pattern in our roads, especially in rainy seasons. That means water and oil doesn't mix, so they form a layer between the two mediums. So we are studying about that. See, what happened means we have the two conditions. So whenever the light, that means monochromatic light illuminated on the film, we have the two conditions for bright and dark fringes. Now it is exposure to, it is illuminated to, that's illuminated by white light, then we have to see, we have seen the different colors. There is also Vibgyor colors. Now how the variation will be means that receives from our eye at a particular position of R and T. That means the inclination of incidence rays. Whenever we are considering a white light, it consists the continuous range of wavelengths. Okay, that the particular value of T and R. In what happens, the particular position of the eye, the waves only certain wavelengths satisfy the constructive interference. Remaining undergoes with the destructive, means those are having the, that means the color will be present in the reflected system with maximum intensity. Those are undergoes with the constructive interference. The neighboring wavelengths having the less intensity. So the colors in thin films concept, the pattern depends upon the thickness of the film and refractive index R, and also it depends upon the eye observation of a human. Okay, so there will be also be certain wavelengths which satisfy the conditions of minima. So not only for the maxima, not only for the high intensity of colors, it's also there is some also certain wavelengths which satisfies the conditions for minima. So such wavelengths colors will be absent for the reflected light. As a result, the point of film will be appear color. Simply, this is a very easy concept. We have to remind that whenever the film is illuminated to a white light, it depends upon the thickness of the film and R, refractive index or angle of reflection, and our eye. Those three are the main roles in the colors of thin films while we are observing the films. Okay.